Welcome friends to this session of our discussion. In the previous session we are discussing about the basic concept of the calculus of variation. So, we have defined the function, functional, increment in a function, increment in a functional. Important in this is the variation of a functional, which we will find if we can define the increment in j as j x t plus delta x t minus j x t. So, this means we are subtracting the value of j at x t point from the value of j which is at the variation of delta x t in the x t we will have. So, to expand this we expand it using the Taylor series, and we find that the variation can be expressed as the first variation, second variation and the other higher order terms, where first variation is defined as the linear term which is del j by del x into delta x t. The second variation is 1 by factorial 2 del 2 j by del x square delta del x t square. So, this variation will become important once we will find out the optimum values. So, we said the optimum at optimum point my del j should be 0, that we will see little bit later on. So, today we will start our discussion with the optimum of a function, means we are trying to find out the optimal value if a function is given. By definition we can define a function f t is said to have a relative optimum at a given point, say t star, if there is a positive parameter epsilon such that for all points t in a domain D that satisfy mod of t minus t star less than epsilon, the increment of f t has the same sign, either positive or negative. This means if we will have a function f t which can vary in a different ways. So, at a given point we will try to find out what actually will be my optimum point. So, if I will select suppose the lowest point which normally we set to be the optimum. So, in that case what we are saying, my t is bounded between t and t star. So, if I will take this axis as a t, so I can say this is my t star point. So, a region we are selecting which is less than what is the region we have taken as the epsilon. So, the increment f t has the same sign. So, this means if I will get the increment of the f t which will be f t minus f t star, that always will be positive if I have a local minima. So, this means all the points beyond this either on this side or in this side will have a value greater than f t star. So, if f t star is subtracted from any value here, then we said my point is a local minima, because local in the sense I have selected this for a very bounded region, because if I will go further maybe my another point can appear here. This may be say t 1 star. So, if I will say in this figure and a region I will select, so if I will expand this region will be can cover the whole space. In that case I say this is my local minima, but my this point will be the global minima. The same analogy we can apply to define a local maxima and a local minima, but in this case f t minus f t star will be less than 0, because at any optimum point, say T2 star, f T2 star is this. So, this is f of T2 star. So, at this point if I will select any point, that always give me the negative value for the increment. So, by this I can define my local minima, and in general I will say I will have the optimum point if where the df is vanishes. So, my necessary condition for optimum of a function is that the first differential vanishes, means that df will be 0. The second differential will be greater than 0 for minima and it should be less than 0 for maxima. Similarly, we can define the optimum of a functional. Here functional is a function of, so j is a function of a function x star. So, what we are saying, let I will have the optimum value of the function as the x star. So, in this case there is a positive epsilon such that all function x in a domain which satisfy x minus x star less than epsilon, the increment j has the same sign. So, this means if x star is my optimal point, then if I will find the increment, then jx minus jx star will be greater than 0, then jx of star is nothing but a relative minimum point. And similarly, if del j is less than 0, jx minus jx star is less than 0, then jx star is a relative maximum. So, if the above relation are satisfied arbitrarily for large sigma, then we say jx star is a global absolute optimum. Optimum means if it is increment is greater than 0, we say it's a minima, increment is less than 0, we say it's maxima. And the increment of a functional, we have seen that this is given as my first variation, second variation and the higher variations. So, naturally if my first variation will set to 0, then the sign of del j is governed by the my second variation, and at optimum point as my slope will go 0. So, when the first variation will become 0, that will be my optimum point and the sign will be governed by the second variation. So, on this basis we will have the fundamental theorem of calculus of variation, which state that for x star to be a candidate for an optimum, the first variation of j must be 0. This means we are saying j is equal to 0 if x star is an optimum point. So, this will be my necessary condition, and as a sufficient condition for minimum, del to j must be greater than 0 and del to j must be less than 0 for maxima. That we can see again from my increment point. If my first variation is 0, then the sign of del j will be governed by the second variation. So, del j should be positive for minima. So, therefore, del to j should be positive, del j should be negative for maxima. So, del to j should be negative. So, that is my fundamental theorem of calculus of variation. At optimum point my del j will be 0, which satisfy my necessary condition, and del to j is greater than 0 if I have a minimum point, and del to j is less than 0 if I will have the maxima point. So, based on this we apply our knowledge of function, functional, increment and variations to determine what is the optimal value of a function x star, which will give me the optimum value for j. So, my objective is, the problem is to find the optimal function x star for which the functional j will have a relative optimum point. So, what I have to do? Basically I have to find the increment. From increment we will find out the first and the second variation. We set the first variation to 0 for my necessary condition, and this will lead to me a differential equation which we have to solve subjected to the boundary condition, and then we will check whether my second variation is positive or negative. If it is positive, this will be maxima, if it is negative, then this will be minima. So, for the given J, we assume, let my x star, I already have say x star. So, let this represent my optimal trajectory x star of t. T0 is my starting point. At T0, let I will have the value as x T0. This is my TF point. Now, once we are solving this optimal problem, we must be defined with the boundary condition. So, what may be the boundary conditions means? What is the value of my function xt at T0 and Tf? Normally, from control point of view, if you will see, xt0 and T0 is defined. Defined means these values are given from where we are starting and what is the my initial conditions. The final condition depends upon the nature of the problem. The first problem we are taking, in which xtf and tf is defined. This means we also know what is my tf and what is my x of tf. So, this is known as the 2-point boundary value problem. So, we are given with the initial point, we are given with the final point. T0, Tf both are given, xt0 and xtf are also given. And so, my optimal trajectory is starting from the T0 and terminating at the Tf. So, at final points I know where is my trajectory. Let us consider a variation of delta xt. So, I can say this is my xt which is not at the optimal point. So, we are considering let there exist a optimal trajectory x star t is starting from the T0 and terminating to the Tf point. We are considering a variation of delta xt in x star of t. My terminal points are bounded. So, my variation is also starting from the T0 point and terminating to the Tf point. So, this is my condition. I am given with the T0 and xt0, Tf and xf, which is the value at the Tf point. This is my optimal trajectory and this is the variation in the optimal trajectory. So, for a given value of the x, I can write j at the x star point and j at the x point. So, to start my problem, my objective is to find out the increment in the j, and by definition increment on the j is defined as j at j x star plus delta x t point minus j at x star of t point. This will give me the increment in j. So, j x star t plus delta x t, and as we have considered v to be a function of x, x dot and t. If I am giving a variation in x t, so there is a variation in the x dot t also. So, that is why we are saying x t plus delta x t, x dot of t plus delta x dot of t, t minus j of x star t, x dot of t and t. So, that is we have considered a journal form of the functional, which is the function of x star t as well as the function of the x dot of t, and we know j is v of x star t, x dot of star t and t. So, this is integral v at x plus delta x point minus v at x star of point. These two integral we can, because their limit is similar t0 to tf, we can combine together and we can write v x plus delta x, x star plus delta, x dot star plus delta x dot star, delta x dot t minus v x star of t, x dot star of t and t. And these, my objective is to find out what actually will be my increment. So, now this first term I can expand using the Taylor series. So, we can write delta j as integral t0 to tf v x star x dot star t. So, I am dropping out the t by writing here because t is repeated. So, I am simply writing as v x star x dot star, this will be x star plus delta x, x dot star plus delta x dot and t minus v x star x and t dt. We are expanding the first term only. So, only the first term we are expanding. Using Taylor series. So, what actually we will get? T0 to Tf so, my first term will be v x star x dot star t. My second is the first variation del v by del x at my optimal point into delta x of t plus del v by del x dot delta x dot of t plus higher order term, and my last term is minus v x star x dot star t into dt. So, in this I can cancel out this term. So, I am left with T0 to Tf del V by del x at optimal point. I can write delta xt plus del V by del x dot delta x dot of t plus higher order terms into dt. V already have been cancelled out. So, we are simply defining the del V by del x dot delta x dot 1 by factorial 2 my higher order term, which is my the second order term plus the another higher order terms. So, del j I can write in this form. The first two terms are basically representing my first variation and this is representing my second variation. So, I can write my first variation as delta j equal to del V by del x delta x plus del V by del x dot delta x dot. So, the first variation will have the two terms, one in delta xt form, other is as the coefficient of delta x dot of t. So, in the next we will try to convert the second term which is in the delta x dot of t form in delta xt form, and this we can do using the property of the integration and integrating it by parts. So, we are considering consider the second term of first variation and what is my second term? That is integral T0 to Tf del V, I am simply writing del V dot by del x dot at optimal point into delta x dot dt. So, we are considering only this term del V by del x dot delta x dot, and this we are integrating by parts. So, we are using say if I will write the duv. So, this is nothing but V du plus u dv. If I will integrate this with the given limit, let us say T0 to Tf, T0 to Tf, T0 to Tf and write this term. So, I can write integral T0 to Tf u dv as minus integral T0 to Tf v du plus. So, if I will integrate this, what actually I am getting? I am getting simply u v T0 to Tf, means u and v evaluated at T0 and Tf point. So, this if I will write as T0 to Tf v dot by del x dot and this I will write d by dt into delta x. So, delta x dot I am writing d by dt of delta x. So, this is giving me the delta x dot and this is multiplied with the dt. So, naturally if dt will be cancelled out. So, this is T0 to Tf del v by del x dot and this I will write d delta x. So, what I say? Let us say this is my u d of v and delta x is my v. So, what I can write from here? So, this is my u dv, u of dv is minus integral of v, v is nothing but my delta x, du means d of del v dot by delta x dot. So, this is the v du plus u dv and u is my del v dot by del x dot into delta x of t, because this delta x is a function of time. So, this means this is also my delta x t, because I have dropped out the t, I am taking this t inside, varying from T0 to Tf. So, this is my case. So, if I will write this is d by dt and I multiply dt here. So, this term I can simply represent as del v by del x dot delta x t T0 to Tf, which is my last term here, and minus integral T0 to Tf delta x t d by dt del v by del x dot into dt. So, this second term I can expand by these two terms. So, and if I will substitute this second term in this form, what actually I will get? So, you can see here, this is del v by del x delta x, this is d by dt del v by del x dot delta x t. So, I can simply write this as del v by del x delta x dt, this is my first term, this is my boundary point minus d by, so this whole represent my second term. So, these two integral I will club together to write as del v by del x minus d by dt del v by del x dot multiplied with delta x t. Now, this delta x t is a common factor plus del v by del x dot delta x t. Now, see what the boundary conditions we have considered. So, in this if we will see, so we have the two terms here, one is the integral term, other is the term with the limits T0 to Tf. So, what is, so if I will place the value of T0 and Tf here, so this is, this variation is at the T0 point and delta x Tf is the variation at the Tf point. So, that is why this boundary condition, so I can say the last term in this expression is giving me the boundary conditions, while the first term giving me a differential equation in d by dt form. So, this is a non-linear equation which I am getting, and another term I am getting as a boundary condition. In our this 2-point boundary value problem, my initial and the final point is, so 2-point boundary value problem, TP-BVP, 2 point boundary value problem if we are considering. So, this means I have the one term delta x of Tf and the another term is delta x of T0, and as we have considered the case at T0 my this value is fixed. So, there is no delta x of T0, this will be 0, and at Tf again my this point is fixed. So, this will be delta x of Tf. So, this means I can set this value to 0, this value to 0, but only in the case of the 2 point boundary value problem. Later we will see the free endpoint problem, in which we will keep the initial point fixed, but we will make the final time as well as the final state to be free. So, in this case if we will consider the 2 point boundary value problem, so my first variation is simply equal to T0 to Tf del V by del x minus d by dt del V by del x dot delta x t dt. And what is my fundamental theorem? To get the optimum value, my first variation must be equal to 0 at the optimum point. So, for optimum x star t to exist, my delta j must be equal to 0. This means my T0 to Tf del V by del x minus d by dt del V by del x dot delta x t must be equal to 0. But this term is with the integral. Now, if we will see, this whole will have the two major parts. One is in this bracket del V by del x minus d by dt del V by del x dot and the delta x t. So, we use the fundamental lemma which is given as T0 to Tf gt delta x t dt equal to 0. Now, in this case my delta x t is the variation which is arbitrary, which normally cannot be 0. So, if delta x t cannot be 0, this means my g t value should be 0. This is called my fundamental lemma. For every function g t which is continuous given as T0 to Tf gt delta x t dt equal to 0, where the function delta x t is continuous in integral, then the g t must be 0 everywhere throughout the integral. So, throughout the interval T0 to Tf, if delta x t is continuous. This we can prove here, let in some interval delta g t is not 0. If delta g t is not 0, x t is changing, g t is changing. So, during this interval, what is my assumption? The product of g t and delta x t dt must be 0, that is not true. So, this is contradicting my assumption, let g t delta x t is 0. So, this means if delta x t is arbitrary, my g t will be 0, and in this case I can say this is my delta x t, and if my g t is this. So, for this integral to be 0, delta x t is arbitrary and continuous. So, my g t will be 0. This means my del v by del x minus d by dt del v by del x dot will be equal to 0. In simple form, we can directly write as del v by del x at optimal point minus d by dt del v by del x dot at optimal point, that must be equal to 0 for the complete interval from T0 to Tf, and this is called my Euler equation. So, I stop my discussion for this session at this point, and more detail of this basic variational problem we will discuss in the next class, and we will also take up an example to see the application of this basic variational problem. Thank you very much.